Understanding binary and hexadecimal, or actually any other numeral system. So, why would we want to learn about binary and hexadecimal or even binary number systems in general? Well, all the computers that we use, uh, they see numbers as binary. And the reason for that is simply because computers need to process very simple information, and representing numbers as in a binary number system, we only have two digits, right? Zeros and ones. And that for computers is very useful. But it's not so useful for us because it's very difficult for us to process this very long numbers. And on top of binary systems, we also have hexadecimal. In fact, there are many other systems that are on the power of 2, hexadecimal being on the power of 16. So before actually delving into these two types, let's first take a look at something that we understand, we are very clear about, which is the decimal system. So how does it work? We have, let's go back to preschool, then we have 0, we have 1, we have 2, 3, and then we go all the way up to 9. And then here, if you remember your preschool math, we sum 1 to 9, and then it becomes 0, and then it rolls to 0, and then the 1 is moved to the next uh, case value. So if you were in school, it would be something like this. You would sum plus 1 here, and then this would be 0, and then here we would get a 10, right? And this one would be rolled over to the next case, and then we would sum it here with a 0 that would exist here. And then we would have 10. So yeah, we get 10. And then we continue like that, right? 11, 12, until we get to 99, where we have the same process, right? We sum 1 here, and then this becomes 10, roll over to 0. This one is sent to the next case, and then same thing happens. We have 0, and then another one is sent to the next case, and then we have 100. And that's how we count and sum numbers in a decimal system. But how is this different from binary? Well, actually, it's not really different. In binary, we would have 0, we would have 1, then we would have 2, 3, 4. And it goes like that. And then we can have the numbers like here so we understand better. But the process that we're doing here is basically the same, except that for each case we only go up to 1. So for example, when we have 1 here, right? If we want to sum plus 1 here, what we're going to have is that we're going to have 1 plus 1, which would be 2. But we can only have up to 1 in one value unit. So this would roll over to 0, and then we would move this 1 from here to the next case, and then we would get 1. And this is the following number that we get, which would be 2. And we just proceed like that, following the same rule. So now that we know how to count them one by one, how do we actually interpret a certain number? Because it's kind of easy to go one by one, but if I give you a number like this, for example, how do we even read that? Well, what we do here is basically something that we can do for any numeral system, which is to actually look at the power of each case. So let's forget about that binary number for a bit and look at this one in the decimal numeral system. Oops, sorry. Which is something that we understand. That is 182, and as soon as we look, we know that this is 182. We don't need to do time to process that. But if you were a computer or if you were learning decimal system for the first time, how we would could interpret this? Well, one way to interpret it is to see each case as a power of the number that the system is based on. So here we would have 2 to the power of 0. Sorry, my mistake. Here we would have 10 to the power of 0 times 2, because this is a decimal system, right? Here we would have 10 to the power of 1 times 8, and here we have 10 to the power of 2 times 1. So what I'm doing here is very simple. I'm getting the base number from the system that we're using, which is 10. Then I'm making it to the power of the case that we have. So it's like this is the first, this is the second, uh, this is the third, right? So I'm making to the power 10 to the power of 0, 10 to the power of 1, 10 to the power of 2. And lastly, I simply multiply to the number that we have in that case. So if we make this sum, right, of these three numbers, we would have 10 to the power of 0 is 1 times 2 equals 2. 10 to the power of 1 is 10 times 8 equals 8. And 10 to the power of 2 times 1 equals 100. And there we go. If we sum 100 plus 80 plus 2, we get 182. Now, this is a kind of like a complicated way to see something that we already know, but we use the same rule for other numeral systems. So going back to that number that I showed previously, how we would interpret this number? We would do exactly the same thing, except that now instead of using 10 for the decimal system that we were looking before, we use 2 for this binary system. So we would have 2 to the power of 0 times 0, 2 to the power of 1 times 1, 2 to the power of 2 times 1, 2 to the power of 3 times 0, 2 to the power of 4 times 1, 2 to the power of 5 times 0, and then finally 2 to the power of 6 times 1. So let's see what this will become. Anything times 0 will be 0. 2 times 1 will be 2. 2 to the power of 2 is 4. Anything plus 0 is 0. 2 to the power of 4, we would have 2, 4, 8. No, sorry. 2. 2 times 2, 4. Then 8. Then 16. Here we would have 0. And here we would have 64. So, what we have here finally? We have 20, 22, we have 76. And basically summing up all these numbers that we got. So there we go. A way of interpreting this kind of complicated number that we have in binary. So we've seen how to count and how to interpret them. Now, what about this hexadecimal system? In the hexadecimal system, our base goes to 16, so not from 1 to 9 like we have in the decimal, but from 1 to 15. And why this thing even exists? Why would be interesting to use that? Well, it is very good for reading binary data. So imagine that we have this word, hello. As you can imagine, the computer represents everything as zeros and ones. So how does the computer actually see the information about each letter? Well, that would depend a little bit on encoding, text encoding, but setting that aside and looking at a common way of storing letters, we would have this. Now, this is very difficult for us to parse, right? It's very difficult to, even if we know that each group each group here of zeros and ones represents a letter, it's very difficult for us to just look at them and see, okay, this represents an L. I can see that these and these are the same, for example. It's very difficult to find patterns in this sea of numbers, sea of zeros and ones. But if we convert this to hexadecimal, then we have this. And I don't know for you, but for me this is much easier to understand. I can already clearly see that we have two letters that are the same, right? It's for C that represents the L. So the idea here of hexadecimal it's exactly this, providing a better way for us to look at binary numbers. And more interesting than that, you may have heard of the word byte before. A byte is nothing more than a sequence of 8 binary numbers. So something like this. Oops. Something like this. The computers often store information as bytes, and in this case we have that one letter is represented by 1 byte. So if we can represent each byte as a kind of like a simplified number like this of only 2 digits, then it's very easy for us to find patterns in this and then interpret any data that we may be dealing with. So how do we count in this hexadecimal system? So we go in a similar rule that we had previously. We have 0, we have 1, we have 2, and then we can jump a bit ahead to 8, 9, and then when we got here, we know that we were not gonna do that process of summing 1 and then roll into 0 and move into the next digit. Instead, we will continue in the same case, and then we're gonna have 10, 11, 12, 13, 14, 15, and then finally here we're gonna have 16. Now this is the the part where it may get a bit confusing, right? Because what we see here is a 10, but this actually is 16. So putting the numbers here to help us processing this information a little bit better. And if we were to continue, we would count exactly the same way. So we would have uh, 17, 18, 19, and we would continue all the way up to 24, 25, 26, 27, 28, 29, 30, 31, and 32. Uh, and to interpret the a binary number, we basically use the exact same root that we had before. So imagine that I have here, don't know, gonna make up a random number. So we have this number in the hexadecimal case. Sometimes we may add this little number to the side to indicate which numeral system you're using. You could also have something like this, for example, for binary, or I don't know, like this for decimal system. So how do we interpret this? Thankfully, I already have the letters here, so it's very easy for us to refer to them. but we basically use the exact same uh, rule process that I showed before. So we're gonna have 16 to the power of 0 times a, 16 to the power of 1 times 3, 16 to the power of 2 times b, and then 16 to the power of 3 times 1. Now, anything to the power of 0 is 1 times a, which we know is 10, will be 10. Here I'm going to write the numbers in decimal so we can understand them a bit better. After all, we're trying to interpret this number. 16 to the power of 1 times 3 will be 48. Is that correct? That is correct. Oh, oops, 48. 16 to the power of 2, which is 128. Sorry, it's 256 times b. I'm having the help of a calculator now because we're getting slightly bigger numbers. We have 2,816, and then we have 16 to the power of 3, which is 4,096 times 1. So there you go. If we sum up all these four numbers, we have finally 6,970. So this is a kind of like a bigger number, difficult to like actually convert into decimal system. But when it comes to computer and interpreting binary data, we're not so much interested in what exactly and what exact value a certain hexadecimal number represents, but we are more interested in the patterns. So when you look at the long sequence of bytes, you want to find the patterns, which bytes look the same, which bytes are different, what's the difference between them. In this case, the hexadecimal case is very useful. And in fact, there are many other uses for hexadecimals. Just one that I will not go very deep in here. I haven't prepared for that. But you may have heard of the RGB system, which is a color system where basically we have a number that represents red, a number that represents green, and a number that represents blue. And we have three numbers that indicate more or less how strong that color, uh, that each component is in that color. So if we have a very strong red, a very strong green, and a very strong blue, we would have white, basically one that encompasses all the colors. And this is often represented as numbers. And because it's easier for the computer, we have to represent it as hexadecimal. So if we have, for example, we know that white is the color that have all the three values up to the maximum, and we know that it's represented by 2 bytes, then we know immediately that white is represented by FF, 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 which would be basically 256 for all the bytes that we have. And the same thing for black, we would just have 0, meaning that we don't have any, all these colors are to the minimum value that we have. And there's word that is often called hex code, which you would see more like this. And this is usually how people in design and I don't know doing web design things, they would represent a color, right? So this would be the color, how they represent the color white. So thank you for watching. If you have any question, please leave in the comments below and I may attempt to answer them.